You're standing in the middle of a frozen wasteland, minus 60 degrees. At this temperature, steel snaps like glass, and your breath freezes in the air with a distinct crackle. You have exactly 7 minutes before your fingers lose the ability to grip anything, and less than 3 hours before your heart simply stops. Most people believe survival is about heroism or luck. It's not. Forget the Hollywood myths about 2 sticks magically turning into a cozy fire. In the Arctic, fire isn't magic, it's pure physics and discipline. If you want real survival systems instead of fiction, subscribe now. Today, we're breaking down exactly how the Inuit transformed this frozen hell into a controlled environment. How do you generate heat when everything around you is trying to freeze you solid? In Arctic survival engineering, moisture is an invisible killer. While you're fighting the wind, the real threat hides inside the fibers of your tinder. In extreme frost, any liquid in the material's pores instantly turns into microscopic ice crystals. This ice acts as a perfect fire extinguisher. It absorbs the energy of your hard-earned ember faster than the ember can ignite the structure. You can have the ideal spark, but if your material is prepared incorrectly, the system will throw an error that will cost you your life. Forget about searching for dry branches in the open tundra. The entire Inuit preparation process begins long before they step onto the ice. They use Arctic willow down or specific lichens, but the secret isn't in the material, it's in the absolute isolation protocol. This is where the concept of the biological dehumidifier comes in. The only reliable source of dry heat in the polar night is your own body. Your tinder supply is always kept in a leather pouch, pressed directly against your chest, beneath all the layers of your heavy caribou fur parka. This is the only way to keep the material in a state of absolute hygroscopy. Your body heat continuously evaporates any trace of moisture, turning the fibers into gunpowder capable of igniting at the slightest touch. This is high-level discipline. The material cannot be exposed to the air even 5 seconds ahead of time. If you take out the pouch and even a single snowflake falls on it, it will instantly freeze into the fiber structure. This will void all your hours of drying work. In the Arctic, there is no room for improvisation. You either fanatically follow the storage system or you freeze. Once the tinder is ready, the most dangerous stage begins, turning a microscopic spark into a real flame. But this process requires surgical precision in oxygen management. There is a myth that modern gear costing thousands of dollars represents the pinnacle of engineering. But when temperatures drop to critical levels, high-tech membranes turn into useless plastic. In the Arctic, a different technology dominates, one proven over millennia: caribou fur. This is not just clothing. It is a complex, multi-level thermal management system. Let's break down the physics of the material. Caribou hair is unique. It is hollow inside. Each strand is a microscopic capsule filled with air. In thermodynamics, stagnant air is the best thermal insulator. When thousands of these capsules create a layer around your body, they form a nearly impenetrable barrier against thermal conductivity. No synthetic fiber in the world has yet been able to fully replicate this porous structure. But the main problem in extreme cold isn't the external environment, it's you. Your body constantly releases moisture. In a standard down jacket, this vapor condenses and freezes, turning the insulation into an icy shell. The Inuit parka solves this through the chimney effect. The garment's cut allows excess heat and moisture to escape through the collar without getting trapped inside. The fur is arranged in 2 layers, one with the hair facing the body, the other with the hair facing out. This creates a double air pocket that functions like a vacuum flask. This isn't just tradition, it is a strict biological heat management protocol. If you wear too many layers and sweat, you're dead in 2 hours. If your clothing is too tight and compresses the air layer, you'll freeze in 40 minutes. The Inuit transformed fur into a high-precision tool that allows a human to stay warm even when the environment is trying to drain the life out of them. Understanding how this armor works separates the survivor from the victim. But even the best clothing is useless if you don't have shelter. In the next part, we will break down ice architecture and the physics of the snow dome. Starting a fire in extreme frost is only half the battle. The other half is retaining that energy. In the Arctic, a campfire without shelter is an engineering failure. In an open space at -60°C, thermal energy dissipates instantly. To turn a flame into a life support system, you need a reactor. And that reactor, perfected by the Inuit over millennia, is the igloo. Forget the notion that an igloo is just a snow house. For Inuit hunters, it is a high-precision thermal insulator. The snow used to build the blocks is 90% trapped air. In physics, this is one of nature's best thermal insulators. But the system's magic isn't in the snow itself, it is in the architecture of the interior space. The key element of the Inuit protocol is the cold trap. The entrance is always dug below floor level. Since cold air is heavier than warm air, it settles in this niche, creating a natural plug that keeps the frost out. When even a small oil lamp or a tiny fire is lit inside, the Inuit trigger a glazing process. A thin layer of snow on the dome's inner surface melts and then refreezes, turning into an ice crust. This layer not only strengthens the structure, but also acts as a mirror for infrared radiation. Heat bounces off the walls and concentrates in the center of the dome, where the occupants are. The result of this engineering design is staggering. While a blizzard rages outside and temperatures drop to -60°, inside the igloo, using only body heat and a small flame, the temperature rises to 0° or even higher. This 60-degree difference is your safety margin, gifted by Inuit technology. However, such airtightness creates a new threat. Without a proper ventilation system, carbon dioxide buildup can kill you faster than the cold. In the next part, we will break down the breathing protocol and tactile navigation in zero visibility conditions. Imagine that the world around you has simply vanished. This is called a whiteout. At -60°C and with gale force winds, the line between sky and earth disappears in seconds. Your vision, which you have relied on your entire life, turns into a useless instrument. In physics, this state is described as absolute sensory deprivation. In such conditions, a human being loses spatial orientation within 10 steps. Without visual landmarks, your brain begins to send false signals, causing vertigo and panic. A directional error of just 5 degrees over a distance of 100 meters means you will never find your shelter. This is precisely where the Inuit protocol of tactile navigation comes into play. For the Inuit, survival in zero visibility conditions is not a matter of luck, but a matter of mechanics and strict discipline. The primary tool becomes the safety rope, often called the thread of life. In Inuit settlements and temporary camps, a network of ropes is strung between living igloos and supply caches. This is an analog navigation system that does not rely on batteries or satellites. The movement protocol is simple and harsh. You never let go of the rope. Your palm becomes the primary sensor, reading the tension and the knots that serve as tactile direction markers. But the Inuit go further. They train their bodies to use additional biological sensors. You learn to feel the wind direction with the skin on your face. If the angle of the ice crystals hitting your cheek changes by only a few degrees, you instantly realize you have drifted off course. This is an engineering approach applied to one's own body. You turn yourself into a human gyroscope. At -60°, you do not have the luxury of a second chance. If you let go of the rope in search of a lost landmark, you are already dead. Your heart just hasn't stopped beating yet. The Inuit system teaches fanatical adherence to the rules. Your hand is always on the rope, your step is always measured, and your attention is focused on tactile sensations, not the empty white space before your eyes. But even if you find your way back, you must face the most dangerous force in the Arctic. In the next part, we will break down the mechanics of defense against the North's top predator and learn why a simple door can be your last chance at salvation. When there isn't a single tree around you and the nearest driftwood is buried under layers of ice, the concept of wood-based survival is completely void. At this point, the engineering genius of the Inuit moves to an entirely different level of resource utilization. To operate a flame system at -60 degrees Celsius, they use the most energy-efficient fuel on the planet, seal fat. This is not just biological waste. It is a concentrate of chemical energy that Inuit hunters have transformed into a controlled source of heat and light. The primary tool here is the kulik, the traditional stone lamp. Analyzing its operation is a lesson in applied physics. The main problem with fat is that in a solid state during extreme frost, it does not burn. To start the chain reaction, you must first change the substance's state of matter. The Inuit use a feedback principle. The heat from the burning wick melts a piece of solid fat placed at the edge of the lamp, turning it into a liquid that then feeds the flame. The wick in this system acts as a power regulator. It is usually made from pressed Arctic moss or willow down. Here, capillary action is critical. If the wick is too thick, it will smoke, uselessly wasting the precious resource. If it is too thin, the flame will lack the power to melt new fat. Hunters adjust the fire line along the entire length of the stone bowl, achieving the perfect balance between light and heat output. From a thermophysics perspective, seal fat possesses a colossal energy density, surpassing many modern fuels. One small lamp is enough to maintain the temperature of life inside an igloo throughout the entire polar night. It is a discipline of resource management, where every drop of fat must be converted into infrared radiation with maximum efficiency. The Inuit system transforms marine animal fat into a shield against absolute cold. However, burning such fuel in the enclosed space of the dome creates a new engineering challenge. Gas exchange physics and airflow management move to the forefront. In the next part, we will break down the ventilation protocol and learn how the Inuit solved the carbon dioxide problem without letting precious heat escape. In conditions of extreme cold, airtightness is your best friend. But in the igloo system, it becomes a deadly trap. We previously examined the glazing process, where the inner walls of the dome are covered with an ice crust to retain heat. However, this ice shell transforms your shelter into an impenetrable cocoon. The problem lies in the fact that both the flame of your oil lamp and your lungs are oxygen consumers. Without an influx of fresh air, carbon dioxide levels begin to rise, and with incomplete fat combustion, odorless and colorless carbon monoxide is released. The Inuit survival protocol includes solving this problem through precision management of airflows. The engineering secret lies in utilizing the pressure gradient and air density. Since warm air, heated by the flame and breathing, is lighter than cold air, it rises to the top of the dome. The Inuit carve a small vent hole at the very apex of the igloo, which functions as an exhaust flue. Through it, stale air, saturated with combustion products and moisture, is pushed outside under pressure. But the system would not work without an influx of fresh oxygen. This is where the cold trap architecture we discussed earlier comes back into play. Fresh, heavy, and cold air from the outside constantly filters through the entrance tunnel. Being below the level of the living platform, it does not mix instantly with the warm air, but slowly displaces the old gas upward toward the ventilation hole. Balance in this scheme is critically important. If the hole in the dome is too large, you will lose the accumulated thermal energy, and the interior temperature will drop below 0 degrees within minutes. If it is too small or becomes clogged with frost, gas concentrations will reach critical levels, and you simply will not wake up. Inuit hunters use the lamp flame as a visual oxygen sensor. If the fire begins to dim or change color to a deeper red, it is a signal that the ventilation protocol has been breached. This is a discipline of managing invisible processes, where the correct diameter of a single hole in the snow separates life from death in the polar night. In the next part, we will move on to the question of mobility. How to transport this precious flame across the frozen wasteland when your shelter is left behind. Mobility in the Arctic wasteland is a matter of life and death. However, at -60 degrees Celsius, mobility conflicts with energy expenditure. We previously examined how starting a fire from scratch requires colossal effort and time. In an emergency relocation or a prolonged blizzard, you might not have those 30 minutes for preparation. Therefore, Inuit engineering thought developed the Eternal Ember Protocol. This is a system for transporting a living flame over vast distances, transforming fire from a stationary resource into a mobile tool. The tool for this task is a portable hearth, often made from a hollow caribou antler or a protected bone vessel. Inside it, an environment for controlled oxidation is created. Breaking down this technology reveals another facet of Inuit discipline. The bottom of the vessel is lined with a layer of densely packed ash, which acts as a thermal insulator, preventing the glowing coal from burning through the walls. Atop the ash lies the core, a large ember obtained from an oil lamp or campfire, wrapped in dry moss and soaked with a minimal amount of seal fat. The primary engineering challenge of transporting fire at -60 degrees lies in oxygen balance. The vessel must be closed tightly enough so that the freezing air does not instantly chill the coal, yet it must have microscopic gaps for an influx of oxygen to maintain smoldering. If the ember suffocates, you lose your protection. If it ignites, you lose the vessel and suffer burns. Inuit hunters carry this container beneath their outer clothing, using their body heat as an additional barrier against the external cold. This protocol turns a human being into a living energy container. Every 30 or 40 minutes, the hunter is obligated to check the condition of the ember, carefully fanning it if necessary, or adding microscopic portions of tinder. This is a continuous process of managing a chemical reaction on the move. Such a system allowed Inuit groups to travel dozens of kilometers across ice fields, with the ability to deploy a full-scale heat station in a new igloo in just a few minutes. Fire did not simply follow the people. It was integrated into their survival logistics as the most precious cargo. In the final part, we will summarize this 10-step system and understand why, in the Arctic, a flame is not an element, but a strict mathematical discipline. We have analyzed the Arctic not as a backdrop for adventure, but as a sophisticated engineering challenge. At -60 degrees Celsius, nature leaves no room for guesswork or inspiration. Only the protocol works here. As we conclude this breakdown, it is vital to understand the primary takeaway. The Inuit survive in this frozen hell not because they are stronger or more resilient than other humans. They survive because they have replaced fear and randomness with the mathematical precision of their actions. Look at the entire cycle once more, from preparing tinder beneath your clothing to navigating by rope in a whiteout, from the physics of the snow dome to the chemistry of seal fat. Each of these 10 steps is not merely tradition. It is a risk minimization algorithm proven over millennia. In a world where any mistake leads to a fatal outcome within mere hours, discipline becomes the only currency of value. For Inuit hunters, fire ceased to be a divine gift or accidental luck after a lightning strike. They transformed it into a managed technology that can be extracted from frozen wood, preserved in a bone vessel, and carried across hundreds of kilometers of emptiness. This revolution in consciousness, the transition from seeking a resource to generating it under pressure, is what made humans the masters of the Arctic. At -60 degrees, your life depends not on your gear costing thousands of dollars, but on how precisely you follow the sequence of operations. Do you understand the physics of heat loss? Can you control gas exchange in a sealed igloo? Are you capable of maintaining calm when your vision is cut off and your only link to reality is tactile contact with a rope? The Arctic flame is a symbol of human intelligence defeating the entropy of cold. It is a system where every component, from the drill's angle of inclination to the diameter of the ventilation hole in the snow, is calculated for one purpose: sustaining biological life in an environment not intended for it. Now that you know these protocols, the world around you will never be the same. You see not just ice and snow, but a field for engineering solutions. But remember, in the Arctic, knowing the protocol is only half the battle. The other half is the will to follow it to the end, when your fingers lose sensation and your brain pleads for sleep. Survival is not a miracle, it is discipline. Thank you for walking this path with us.